Hello everyone, my name is Magnus Madsen from Aarhus University, and today I'll tell you about semantics for the essence of React. This is joint work with Ondřej Lhoták from the University of Waterloo and Frank Tipp from Northeastern University. So let's talk about web applications. So traditional JavaScript web applications were written as a combination of HTML and embedded JavaScript code. So to provide interactive features, this JavaScript code embedded in the HTML would perform direct manipulation of the document object model, for example, inserting elements or deleting elements. The problem with this approach is that it's very unprincipled, and so it easily becomes brittle, and it's also very non-modular. It's hard to sort of reuse code. Moreover, it's often non-incremental in the sense that if a small change occurs, that might still cause large parts of the page to be re-rendered. The React framework aims to overcome these issues. So React web application is a collection of declarative components. And these components are modular and reusable. Moreover, React itself provides a way to incrementally re-render components in response to state changes. So today we'll talk about a formal semantics for the essence of React. So I just want to say that even though we are looking at React, there are many so-called declarative UI frameworks that adopt this kind of programming. So there's of course React, then there's Preact, there's SwiftUI, and there's Vue.js, and many others. So while these do not all operate in the exact same way, many of the ideas are similar. But today we'll focus on React. Okay, so React in a nutshell, a React web application consists of React components, and each such component has three important constituents. So a set of properties, which can be thought of as input parameters that are used to configure the component, an internal state, which may change over time, and a render method that specifies how this component should be displayed in the browser. And it does so by returning a combination of other components and HTML elements. So to give you a simple example, imagine that you wanted to write a React component for this digital clock here. So the properties for this clock, for example, could be the colors of the individual digits, here red. The internal state could be the current time, which is obviously changing over time. And finally, the render method could be something that returns, in this case, maybe 4 components corresponding to each digit here of the time. Okay, but let's look at an example of how you actually write a React web application. So I want to write a small application that can render a to-do list like this. And so the to-do list consists of work items, for example, answer all my emails, and personal items, buy milk and buy eggs. So starting sort of from the bottom, I'm going to have a component for an individual item, and this component is going to have a render method that just returns a list item tag with the name of the to-do item. Then building on top of that, I'm going to have a notion of to-do lists. So this is something that is given two properties. So one is the title, for example, work items and personal items. And then it's also given the set of actual items to do, and it's going to map over those, building a list or an array of to-do item components. And finally, I have the to-do app itself. So the to-do app itself has a constructor and a render. So the important thing is that the constructor sets up the state. So in this case, it's an object that has a field work with an array of the work items, a field personal with the personal items. And then it has a render method where it's returning this to-do list component twice. Once it's passing in the work items, and the other time it's passing in the personal items. And now the important part here about React is that, let's say for some reason that the personal items change. So maybe I complete one of these items, so the list is now smaller. Well, what React will do is that it will call render to re-render the to-do app because a state change has happened. And then it will discover that these properties has changed, but only for the personal items, not for the work items. And then it will go and it will ask the to-do list to re-render, and that will again return some components here, a smaller list, and then it will reconcile that with how the list is currently displayed. So in this case, maybe one of the items will disappear. And this is done by React automatically. Okay, so two central ideas here in React, and especially in our formalization, are component descriptors and mounted components. So a component descriptor is essentially a class name or a tag name, and then an object that represents a set of properties. And importantly, inside this properties, there is a render method which describes how this component should be displayed. Now, a component descriptor is something static. A mounted component is when you take a component descriptor and you turn it into an object that has an address in the heap and that is actually being displayed somewhere in the browser. And so mounted component descriptors are of the same shape, except that now there's also an address in the heap associated with it. And so there are two ways a component descriptor becomes live, if you will, is through mounting or through reconciliation. And importantly, both component descriptors and mounted components are values that can flow around in the program. In this work, we formalize an operational semantics for sort of the essence of React, building on the lambda.js calculus. And so configurations in our semantics look like this. So the first component is the heap as a standard. Then this component here is what we call the next component state. So I won't go into more detail about that, but it holds the next state that will be used when a component is rendered. Then we have a map of mounted components. This can sort of be thought of the virtual DOM. We have a map of event listeners, and we have the current expression. Then, as I explained, we have component descriptors and mounted components. So component descriptors have a name and a set of properties, and mounted components have the same, but also an address in the heap. And these are values in the calculus. Then the calculus consists of a whole bunch of internal control expressions that are used to express the semantics of React itself. So these are things that the programmer does not write, but that just controls the execution. All right, so let's talk about mounting and unmounting. So this is the process where you have a component descriptor and it gets turned into a mounted component and possibly later destroyed. So here on the right, I have the operational semantics, but I'll not go into detail here, but instead refer to the paper, but I will show you an example. All right, so let's consider this simple example where I have a component descriptor here, pi1. It's a form and there are some properties. And crucially, inside the properties here is a render method. And this render method is going to return a list of component descriptors. In this case, it's just a list with one element, pi2. Now, what is pi2? Well, this is a button component descriptor. It has its own set of properties. It has a render method that returns the empty set of component descriptors. So sort of informally, intuitively, what we have here is a form that inside it contains a button. And so the way this program is evaluated is that we can take the top level component pi1 and inject it into the empty program, which gives us this configuration. So all the maps are empty because nothing has been allocated in the heap and no components have been mounted and so forth. And what we're going to do is that we're going to mount this component descriptor, and afterwards we're going to return to the event loop here indicated by a dot. And it's in the event loop that the user can press buttons and so on, which causes life cycles to be invoked on components, which can cause state changes, which then cause components to be re-rendered. All right, so this mount expression here is going to reduce to this expression down here, mounted, and then of this form component that's now been given an address. But the more interesting part is this inner expression here, which is saying that, okay, now we have to render on A1. So A1 is this form component. And this is going to return some component descriptors to us, and then we have to mount that sequence. So when we have this and take a step, well, render here, calling that returns, as we saw this list here of component descriptors, pi2. Then to mount a sequence, well, we just split it up and we mount the first component and then the rest. And so I'm not going to show you all the steps, but in the end, we're going to end up with a configuration where we have entered the event loop, and these components have been mounted and been set up appropriately in the virtual DOM. All right, so let's talk about reconciliation. So this is the process of merging a component descriptor with a component that is already mounted. And so here I have the rules, but again, I'll just illustrate by example. So let's consider a case where we have this mounted component here. So we have a button, it has some address in the heap, there's some text submit. And now we're reconciling this mounted component with this component descriptor here, alert text submitted. So what's happened here is that some change has happened, and now the render method of some component, instead of returning a button, is now returning this. Now, in this case, the two components have a different name. So button and alert are different names. So that means that we have to unmount, so destroy the button component, and then mount alert in its place. And that's captured by this reconcile different root rule. So during reconciliation, when the names are different, that means we destroy the old component and mount the new one in its place. On the other hand, it could also be the case that we have a mounted component, some page with some name about, and then now we want to reconcile it with this component descriptor, which is the same. So in that case, we are not going to unmount the component and remount something else in its place. Instead, what we're going to do is that we are going to re-render this component, now passing in the new properties. And of course, re-rendering it will return a list of component descriptors, which we then have to reconcile with its current children. So this is sort of a recursive process where we're re-rendering and then reconciling and then re-rendering and so on. And this is captured by this rule RC same root. Okay, finally, let's say there's a situation where we have the empty list of mounted components, but now we discover that we want to reconcile this with actually a sequence of some component descriptors. Well, in that case, it's easy. We just need to mount these extra component descriptors. So this is captured by the RC extend rule. And there are other rules that handle other cases when we are trying to reconcile lists where there are too many or too few elements. All right, so this sort of illustrates some of the core ideas behind how mounting and reconciliation works. So one thing we would like for our calculus is that we want these operations, mounting, unmounting, and reconciliation, they should terminate after some number of steps. Because if they don't terminate, that means we never reach the event loop. And if we never reach the event loop, that means you can't actually interact with the app by clicking a button and then having some state change happen. So for this to make sense, we really have to reach the event loop. However, it is possible to write React applications where we never reach the event loop. So here I have an application where I have a component descriptor and it's A, and its render method returns a component descriptor for B. And B is also a component descriptor and its render method returns A. So intuitively, this is a component that has a subcomponent B, that has a subcomponent A, that has a subcomponent B. So trying to mount one of these component descriptors will trigger an infinite loop of mounting operations. And so what we want to do is that we want to rule out these programs. So we want to impose some requirement, and when this requirement is true, then we can prove termination of these processes we have defined. And the notion we need is what we call K well-behavedness. And so if a React application is K well-behaved, then mounting, unmounting, and reconciliation will terminate. Now in this work, we have not looked at how to actually automatically prove that, but that would be interesting future work. And the intuition behind this K well-behaved concept is that we want to avoid this situation. So sort of intuitively, the render method of A should only return smaller component descriptors according to some ordering. Because if we always return smaller component descriptors, well then eventually we'll not be able to return any and the process will stop. Okay, so to make this a little bit more formal, we define a rank as a function that maps component names to natural numbers. And then we say an expression E is K well-behaved if it evaluates to a list of component descriptors pi over bar, such that for each component descriptor in the list, we have that the rank is bounded by K. So that means you can, an expression E that is K well-behaved has to return component descriptors of strictly smaller rank. And so the special case is when K is 0, that means, okay, so now you have to return the empty list, and that means you don't have any children at all. All right, and so with this definition in hand, we can lift it to component descriptors, saying that if you have a component descriptor, it has some properties. Inside there is a render method, and this render method is an expression, and so that render expression must be K well-behaved. And so using these definitions and a couple of others, we approve theorems such as this: injects well-behaved, mounting preserves well-behavedness, unmounting preserves well-behavedness, reconciliation preserves well-behavedness. So in other words, if your React app is well-behaved, then these processes will terminate. Just to give you an example, here is the theorem for mount preserved well-behavedness. So saying we have some well-behaved component. We have a well-behaved component shape map. This is the virtual DOM. Won't go into detail about that. Then if we are in some configuration, in some evaluation context, we're trying to mount pi, then we will be able to take some number of steps to reach another configuration with updated maps, where this mount has been reduced to a value to an address. And everything is still well behaved in this configuration. All right, so in summary, we talked about how traditional JavaScript web applications were written as HTML with embedded JavaScript code, but this was very fragile and brittle and non-modular. React and other declarative UI frameworks build on this idea of reusable components. And we have presented a minimal calculus lambda React that tries to capture the core of this React framework, which is mounting and unmounting of components, reconciliation of component descriptors and mounted components. And in the paper, we also talk about how to handle state changes. Finally, we have defined this notion of well-behavedness. And so if we have well-behaved components, then mounting and unmounting will preserve well-behavedness, and reconciliation will also preserve well-behavedness, and these processes will terminate.